Yeah, but the streaming seems to be bad because it's a little delayed. Hello? So, good evening, everybody. Yeah, but the streaming seems to be bad because Yeah, but the streaming seems to be bad because Hello? Hello? So, so, good evening, everybody. Good evening, everybody. Yeah, but the streaming seems to be bad because Yeah, but the streaming seems to be bad because Hello? Hello? So, good evening, everybody. Good evening, everybody. Good evening, everybody. Yeah, the streaming seems to be bad because Yeah, Hello. Okay, maybe it will start working. So, um, good evening, everybody. Good evening, everybody. Hello. Hello. Maybe. Okay, maybe it will start working. So, um, good evening, everybody. Okay. Hello. Okay, maybe it will start working. So, maybe let us start with this and then see how it goes. And then if there is a big trouble, then we can actually redo this. So thank you all for joining today as well as joining the course. And I hope you are enjoying the course so far. Maybe let us start with this and then see how it goes. We are then if there is a big trouble through with the first 4 weeks. Redo this. And there have been a lot of response in the joining today as well as joining discussion forum as well, and I am very happy to see that many of you are actively participating in it. Maybe let us start with this. So we are kind of in the next with the peak first 4 weeks, winding up the nuclear physics part. There have been a lot of response. I'm going to start the particle physics part of the course. That many of you are actively. So we thought that this live session is going to help you in sorting out any of the difficulties that you have so far. Winding up the although the discussion forum have been there, maybe this is a good interesting thing to particle physics part of the so course. You had already put, many of you have already posed some of the questions in this which I have had a look at difficulties that and you have. What I will do is to try to address those first and then take up the questions that is coming up in the chat. So you had already put, many of you have already posed some of the questions in this which I have had a look at difficulties and what I will do is to try to address those first and then take up the questions that is coming up in the chat. So you had already put, many of you have already posed some of the questions in this which I have had a look at difficulties and what I will do is to try to address those first and then take up the questions that is coming up in the chat. So you had already put, many of you have already posed some of the questions in this which I have had a look at. So one question from Tuhin and a related question from Shabashti is that why don't we see bound states of only neutrons, or only that of protons? Say, for example, diproton, two protons, or two neutrons. Okay. So basically, this is very important question. This has to do with the nature of the only neutrons, or strong force which holds this together, two protons. The nature of the force is okay. So basically, this is including its very important question parameters. Like we know that it is attractive. The nature of it could be something like strong force which holds this together, two protons. The nature of the force is too much of disturbance. I hope some of you can at least hear what we are saying. Including its very important. Okay, if you look at the strong force, then the nature of it could be, for example, in the very elementary way of looking at it. If you look at the nature of kind of a square well potential, some of you can at least then we see that there are these parameters there. That what is the strength of the strong force that it attracts. So this, for example, in the very what is the value of that? What is the strength of this? What is the strength of strong force? Kind of a square will dictate how the couplings are. Then we see that these are to be fixed from experiments. What we do is to see that we don't really see any of the value of that. What is the strength of dineutrons or diprotons, etc. Therefore, we adjust the parameters such that their binding energies are slightly uh, smaller than what is required to have these diprotons within the present setup, the theoretical setup, or the force that we consider as. How do we get this force or the values of the parameters is from the observations of the nuclei, various different nuclei that exist. So when we fit all these things to these things, we get these parameters, and then when we, with the present understanding, we don't have. Hi Rekha. Something seems to have gone. YouTube video has to be pressed. How do I hear then what I am saying? Oh, okay. Okay. Okay, fine. Perfect. Yeah, so maybe that is the reason, is it? Okay. Should we start again? Yeah. Yeah. Hello. Sorry for the interruption. Okay, let me say that again. So the strong force, the nature of it, as well as the parameters involved in it, what is the strength of it, etc., are basically decided by the observations that we have. And these observations are the observations of the bound states of the nuclei. So since we don't see the dineutrons or the nuclei with only neutrons or only protons, this particular aspect and how we have not, I mean, this observation is not gone into the fitting to get the values of the or parameters of the nuclear force. Now this, then when we look at it, when we use this particular theoretical setup, therefore, we don't have any way of getting the dineutrons or purely neutronic bound states or purely protonic bound states. So this doesn't mean that we are not looking for this or trying to see if there are such states present. There are experiments which are going on to actually look for particularly dineutron or bound states with 4 neutrons, etc. Within certain nucleus or the decay of the nuclei, but we have not seen so far. There have been some hints of dineutron detection, but I don't know how confirmatory those are. It doesn't look like it is really confirmed. The only neutron alone states that we have are the neutron stars. So neutron stars, but there the setup is completely different. It is a completely highly dense system, and we have a different dynamics that apart from the nuclear force that will play a role there. So I mean, it's a gravitational interaction has to be included, etc. So apart from that, whatever the purely nuclear strong force is concerned, so far our understanding is that the dineutrons or diprotons or any such bound states purely with neutrons or purely with protons do not exist. Okay, so moving on to the next question. Why is the Schrodinger equation so important in this thing? I mean, this is kind of straightforward because these are subatomic particles, the nuclei, and the quantum mechanics we know is the principle that we have to apply there. The physical principle has to be not that of classical mechanics, but quantum mechanics. So whenever we have quantum mechanics, then we have to go by the rules of that or the equations related to that. So that is the Schrodinger equation. Hope that is clear. And then there's a question on the energy levels. So the question, let me read for other students. So this is from, again, Srabashti. And question is, let the energy of the nucleon without the spin orbit coupling be E0, and then the spin orbit potential is given as some V spin orbit divided by h bar square L dot S. That is what we have been considering. What is the energy of the nucleon in each of the possible spin orbit configurations? So what this is again discussed in Crane in detail. So but the answer is that this spin orbit coupling interaction will add to an energy term which is V S0 by h cross square, which is the constant coming along with the L dot S, and then you have the total angular momentum J square. When I say J square in quantum mechanics, it is J times J plus 1. So J square minus L square minus S square. So this is the one that we can use to get this splitting. Okay. So what we will do is to actually post the answers that I am telling here sometime later, so that these equations are also clear to you. Okay. So this will tell you that for different J values, so for a particular L value, you have two different J values that are possible because of the spin. And then for these two different J values, there will be two different contributions that will come to this thing, because it depends on the J here. Okay. All right. So then there is a question on what are leptons. We are going to come to the details of this leptons. What are leptons? What are quarks? And then what are the dynamics soon, starting from maybe next week or the week after that, I guess. Next week is going to be detectors and things like that. But the week after that, we are going to start this week 6, I guess. But the short answer is particles like electrons that we already know, then neutrinos that we came across with in the beta decay. There are particles like that which are called muons, tau leptons, etc., which do not take part in strong interactions. They are all called the leptons. Okay, we will come to the details of this later. Another question from Rakesh is, does the neutron possess magnetic dipole moment, although it is a neutral particle? Yes, in fact, sometime back there was a question on this in the discussion forum, I guess, and then Alalika had already explained it. But basically, if we have a neutral particle, which is a point-like particle without any structure, then it is not possible for it to have any kind of magnetic moment. But here neutron is not a it is not an elementary particle. It is bound state of quarks. There are charged particles inside the neutrons, and because of that, the spin of the charged particle inside the quarks inside the neutron will cause some magnetic moment. Also, their other orbital motion will cause the magnetic moment. So that is how the neutrons get magnetic moment. So then we have a question again from Rakesh has two questions. So the second question is, how can the order of the nuclear energy levels be remembered? Yeah, actually, I mean, it is slightly difficult to get the exact expression for the energy level. In this case, it's usually for the Woods-Saxon potential that we have. It is kind of numerically obtained. I mean, you can get it. It is not an easy way of doing it. So I'm not sure how you would be able to remember it. What we will do in the exams, etc., is to actually provide these energy levels. Definitely, you don't have to remember it. So I think it is not kind of necessary there. Okay, why does an accelerated electron radiate energy? That's again a very good question. So, I mean, let me give you kind of a heuristic kind of a picture, like exact reasons and how it happens slightly beyond what we have been discussing here. It requires advanced electrodynamics, and but we can think about this in this fashion. If you have a charged particle which is sitting at rest, then we only have the electrostatic force. But if we have also motion or the charge particle is moving, then we have a current associated with this and therefore magnetic field. So we have an electric force and magnetic force there, so or electromagnetic force associated with a moving charge. And electromagnetic force usually actually radiates, but charge particle moving with constant speed does not kind of radiate. This can be also understood in a way like the special theory of relativity says that the different frames moving with relatively in motion, but if the speed of this is constant, that if there is a frame at rest and then if something is moving with respect to that at constant speed or constant velocity, then it is the things that is happening in these two are to be equivalent. In one frame, if it radiates, the other frame also it should radiate. Now, since the two frames which are relatively in motion with constant speed are such related like that, we can always go back to the rest frame and then say that it is equivalent to any frame which in which the particle is moving with constant speed. But the accelerator, therefore, there is no real way of getting the radiation there. But accelerated frames are different. There is no such equivalence, etc. So accelerated frames will radiate in a way. Okay, I know that it is not completely satisfactory, but what you have to do is to wait for your advanced course in electrodynamics. There you will see how exactly it happens. So there is something called a Lama formula, which actually takes care of this or tells us how the radiation happens and what is the amount of radiation, etc. So it is all precisely computable thing in the electrodynamics that we are now aware of. Now we know. Okay, so the next question that we have is okay, something slightly different from the course, whether MATLAB is useful. Yeah, I think any tool such like MATLAB, etc., will always be useful. But for particle physics, we don't usually use MATLAB, but what's called Mathematica is more useful. But my advice to you all presently is to focus on physics, not only this course, but all courses. That will be, and understand the physics part better. And the tools, whatever tools that you need, you will be able to pick up as and when required in your course, when you start your research. So don't worry about that at the moment. All right, Tuhin has one more question, which is again directly related to what the course is dealing with. The electron capture is also known as the K capture. Why is it so? Okay. It's simply because the lowest or innermost shell of the atom is called the K shell. So this is another nomenclature. N equal to 1 shell is called the K shell. You might have heard about K shell, L shell, M shell, etc. So whenever the electron is captured from the K shell, it is called a K capture. I think it is as simple as that, I guess. Okay, so let me take a few questions from the chat now. What is a square well potential? Okay, why is it necessary to understand nuclear scattering? I'm just picking up something from somewhere. Okay, well, square well potential is something which we all deal with in the elementary quantum mechanics course. So basically, it says that there is a region in which there is a potential. Beyond that region, there is no potential in that. And the potential within that region is constant and negative. But basically you can, it's an attractive kind of a potential. So in the nuclear scatterings, usually the nuclear potential is an attractive potential. This is in a crude approximation. This is the nuclear potential can be considered as square well potential. Okay. More about the square well, etc. You can look at some of the quantum mechanics, elementary quantum mechanics book. So that's why we did not really go into the detail there. Why nucleus does not have a dipole moment? Quadrupole moments. There are many questions like, okay, let me start from somewhere in the beginning, okay? And then try to attempt as many as possible. See that there are also questions in the okay. Okay, so let me start from here then. So, why isospin does not interact with angular momentum? Okay, so yeah, there could be a bit confusion over what is isospin, what is yes, is it? We have not explained it into great detail, maybe, but let me try to address this question. Although we call it isospin, that part is not related to this particular quantity, is not really related to the motion of the particle or the coordinate, nothing to do with the space-time or any such this thing of the particle. It is an intrinsic property of the particle. Therefore, it doesn't really add to the angular momentum of the particle. It is a different quantity. Only thing is that mathematically it is equivalent to, or it behaves like spin. Okay, so isospin will not really interfere or I mean need not to be considered when we are considering the total angular momentum of the particle. Only the spin and orbital angular momentum. So it happens in a, it's not the spin you can imagine as kind of an angular momentum which is happening with, okay, spin of a top, if you take that, it spins on its axis, etc. Although this analogy is not exactly the same as that in the case of elementary particles, which has no size, this quantity behaves exactly similar to that, which means that it is going to add to the total angular momentum. Whereas isospin has nothing to do with this actual spin of the particle. The name can be a little bit misleading for people who are, I mean, when we are introduced to it, but you just, I mean, for the time being, take it as completely a different quantity, and therefore will not really add to the total angular momentum. Okay, so in order to obey angular momentum, rotational invariance requires that the scattering process or decay process Usually, this angular momentum is conserved. Conservation of angular momentum is there in all processes that we consider. Any process, any kind of scattering or decay or any transition that we consider, there is a set of initial state which goes to a set of final state. It could be a de-excitation of an excited nucleus, like what we have been discussing. The gamma decay, or it could be a beta decay where new things happen, or it could be an initially two particles or a neutron colliding with a nucleus and then something happens, some new particles or new nuclei are formed. Any of these reactions or any other such reactions with particles, just electron and proton, etc. also, angular momentum is conserved. It is similar to conservation of the linear momentum. Okay, energy, conservation of energy, conservation of angular momentum, conservation of the linear momentum, etc., are all always kind of considered to be required in any of these transitions. Dipole moment. Okay, I think we will not go into the details of this. So, we can actually look at the textbook for details. I think the crane actually gives a lot of details of. I did not really want to get into the details of the dipole moments or the quadrupole moments or any such thing. So basically, you can go through it, and then if there is any specific, kind of questions beyond what is there discussed in the crane, then we can discuss at some point. Okay, because it's not really. We will not really be able to go into the great details of all aspects there. Schrodinger equation gives the total energy of the system. Pretty helpful. Some of the questions, if I am not able to really understand what it is, so if I am not able to answer some of these questions, kindly pause it again in the discussion forum. We can discuss it there. Then I will be able to answer, or I'll see if the chat actually stays here. I will try to actually ask you what exactly is the question addressing specifically to this paper. Radioactivity of an isolated atom is special one or not? Yeah, so this is a question that is given in the assignment, I guess. I don't remember now whether it was the past assignment or the assignment which is due, right? Which is due. Yeah, so and maybe it is also discussed there. So it's basically radioactivity is a statistical phenomena. So if you take a particular atom, you can only talk about the probability. You won't be able to tell anything about when it will decay, right? And then so it may stay there forever. Nothing contradicts if a particular radioactive atom, isolated, stays much beyond its mean lifetime. Okay, it doesn't contradict any of the theoretical understanding that we have. But we can definitely tell the probability for it to happen. Okay, and the probability is can be understood when we take a large number of these atoms. Then we can definitely say how many of these, plus or minus approximately within an uncertainty, how many of this will decay in a particular sample. Okay. Strong nuclear interaction. How come scattering process and decay process conserve isospin? I think this is again coming from observations. It is like the conservation laws are kind of not derived from first principle, but it is kind of taken as a starting point. It is like, well, at least for our course or the level at which we have been discussing. There are more fundamental, like it is like asking, why is electric charge conserved in any reaction? We don't really have an answer. Of course, there is a more fundamental question about why is it so in nature. We don't address that here. So isospin is also similar to that. It is seen that isospin is conserved in nuclear reactions, the strong nuclear interactions, and we have not seen any violation of this particular concept. Okay, it's from observation. How to calculate the excitation energy of a nuclear shell particle? It's basically, yeah, as I said, we are not really given the expression for the energy levels here. All those things would actually take us beyond what we intend to do in this course. So, but definitely there are. I mean, these are all calculable, and then people have calculated different energy levels. So, if you know the actual energy, the energy values of different energy levels, then you know what is the excitation energies of the nucleus. Okay, some of you have asked for reference books, etc., which I think we will try to see if something more can be added. Crane is a good book. I mean, it is a standard book. It's an old book, but it is still a standard book in overall. Globally, in many places, it has been considered as the thing. So you can rely on that, but I will see if there are more references which I can forward. All right, so then there are some questions on beta decay happens. It happens the decay of the proton surface of the nucleus or the okay. The question is in beta decay whether it is the new protons at the periphery at the surface which decay or within inside that this thing. We can't say this. Which proton is decaying? It is kind of difficult to figure that out. Okay, it could be the proton inside or it could be the proton from outside, etc. Well, if one really go by the position of this away from the center of this, one can actually say that it can also be related to the angular momentum, orbital angular momentum, because the electron emitted from the periphery may have larger, at least a possibility of having larger angular momentum, etc. So I don't know if these aspects are really put in the beta decay discussions. I mean, it's very hard to actually incorporate those. It's the modifications that this will give will be within the uncertainties of whatever measurements that you can do. So I have not seen anywhere this question is addressed. So for the time being, we don't really ask in a particular reaction where this is coming from. It could be any of the protons. Mean lifetime is the average lifetime. Some atoms decay before that limit. Some of them are. It is, okay, so this is the answer to that question, I guess, earlier. Somebody has posted. Okay, good. All right. So beta minus particles come out of the nucleus. So beta is the electron. Electron is, it's not tunneling or anything. There is no previously formed electron inside the nucleus. It is that the electron is formed at that point. It is the neutron which will actually convert itself into a proton and an electron. Okay, so it's different from tunneling. Did all the possible excited energy states have been observed experimentally? I mean, I don't know what exactly is the meaning of this. The other way around, what we do is to actually observe the excited states. Yeah, I mean, okay. Question is, I mean, I'm not saying that question is not sensible. The question is that suppose within the shell model, if there is any particular excited state possible, is that observed? I guess that is what is the question. More or less, I think. So, I mean, there are a lot of models. The shell model, as we have been discussing, is a bit of a basic model. I mean, it is not a complete model. So, there are to be quite a lot of additions or modifications to it, as we have indicated in the course, in the lectures, not really discussed in details, but kind of indicated that, say, for example, the vibrational modes of the collective nucleus or other such energy modes have to be kind of included. And this has been done in the model building. So it's a kind of a process which is going on, refining and refining. So certainly there are many predictions of the shell model which are not really observed, like including some of the excited states. But usually the question that we ask otherwise is also like all the excited states of this, all the things that is observed are to be accommodated. So that's something which the refined models would definitely do, not just the simple shell model. Okay, so I want to take this, I mean, address this question on the Wigner-Eckart theorem, etc. So it's there, it's a topic in, so somebody was asking Wigner-Eckart theorem to determine, can they use this to determine the ratio of the scattering process in decay process, etc. Wigner-Eckart theorem is something which comes in the advanced quantum mechanics. So somebody is asking, what is the Wigner-Eckart theorem then? So we don't really want to go into those this thing there at the moment. We are not going to use any of this in this course. How will nucleon get excited? There are so many configurations. Yes, so it's similar to the atom also, where we have many atomic electrons. So how does an atom get excited? It is somewhat similar to these things that we can think about in the case of nucleus as well. Okay, at least in the shell model. Since neutrons and protons are made up of quarks, how are they able to convert themselves into an electron, which is a lepton? I think you wait for a little while. When we come to the particle physics course, we will tell this in a little more detail. But basically, this quantum field theory allows such kind of creation of new particles where they don't exist before. Okay, and it's kind of facilitated by the special theory of relativity, where Einstein's equation the famous energy momentum relation, energy mass relation, tells that if mass m is related to energy, E is equal to mc square. So incorporating this, one can actually create matter with certain amount of mass from some kind of a radiation or an energy, or previously existing any kind of energy form, including some matter. We'll come to the details of that later. Will the mass of an atom reduce to half at half lifetime? No, it doesn't happen like that. It's not one atom which is reducing to half of it. It's one atom which is going to convert into something else. And half-life is related to a big sample of particles, radioactive materials, where there is some 1000 elements existing, say, present now, will be reduced to 500 or plus or minus 500 elements after half time. But a particular atom element, etc., will remain as it is. Whatever remains, it will not be, its properties will not change. Addition of angular momentum, why don't we consider Klebsch-Gordon coefficient? I mean, we do consider these things. Again, as I said, I don't want to go into the details of quantum mechanics because we are not using it. So it's all useful concepts, but we don't need any of those at the moment here. Okay. How to calculate the excitation energy of the nucleus in nuclear shell model? Yeah, I already told this thing that we don't really, we have not gone into how exactly the energy levels, energy values are considered. Okay. Okay, so if the proton of the hydrogen atom captures its electron, would it become a neutron? Yes, that is exactly what happens in the electron capture process. Okay, so I think that's the kind of questions that we have. There are some questions in this thing that we have posted in the Google Doc that you have given. What's a Higgs boson? We will come to that later. Explain the theory of numerical algebraic. What does okay? Why deuteron has no excited states? I think that's not correct. It can have. Let me see if there are some questions. Okay, so I think we have no more questions. So, okay, let me leave the questions now. I think the chats, we are almost kind of going to close the session. So before doing that, so let me leave the chat questions. And if you have more questions, please post it in the discussion forum. We will try to address those things, okay? But in the coming days, some of these questions that you have in mind, like about the particle physics or any other, what's a lepton, etc., or isospin, strong isospin, and how that is really taken care of. These questions would be addressed in the lectures that we are going to have in in the particle physics section from week 6 onwards, I think. So, looking forward to you all joining the or continuing the excited discussions. Okay, and thanking you for joining today as well. Bye.